Hello everyone. In the video today, we're going to try to finish lecture 8 about discrete choice modeling. The video will focus on the estimation of coefficients applied for the multinomial logic model. First, let's recall the multinomial logic model that we learned in the previous class. And the formula here describes the probability that we're going to choose model I from the set of Cn. We have several assumptions for this equation. First, all the individuals are utility maximizer. They are trying to maximize the utility they're going to choose for the mode. Second, the utility can be specified by the sum of the deterministic component and the random component. And third, the random component follows the IID Gumbel distribution, and the Gumbel distribution is a standard Gumbel distribution with the parameter of 0 and 1. Finally, this is not a mandatory condition, but usually the deterministic component is linear in the parameter. So Vjn is the function of the observed variables xj and a set of the coefficient theta. We have several issues to be solved. First, we want to find out the way to estimate the parameters theta n based on the values of the variable that we can observe. From the probability of the multinomial logic model, we can see that the deterministic utility cannot be observed. In the probability expression, we also cannot observe the probability for us to choose the mode I. What we can observe is the outcome, whether the mode is chosen or not. That is 0 or 1. The second issue we're going to solve is the aggregation. We want to define the elasticity of equivalence. And third, we're going to find out the independence from the irrelevant alternatives properties. And first, we want to extend this model to choice combination, which means we're going to try to understand the nested structures. In this lecture, we'll focus on the estimation of the parameter theta n. Before MNL estimation, we will have a quick review about the estimation problem. This is the general formula for the equation that we can apply for the parameter estimation. We can also rewrite this equation to a random format. Here, y is a dependent variable that we can observe. X is the vector of independent variable which can also be observed from the sample. And theta is the vector of the parameters that we want to estimate, and usually they are known. And psi is the vector of disturbance, and that will be the random term applied in the model. Usually, we know the formula f psi with certainty. It contains some random variables inside. Second, the parameters are totally unknown, and we want to estimate their values. And third, we will have an assumption about the distribution of the random terms psi in this formula. Our goal is trying to complete the model estimation to find out the values of theta. In summary, we will have y as a random variable, which has a combination of deterministic component and the random component. And x is the vector of known variables, and it could be observed, but it will influence the distribution of y. That is, y is determined by a function of x and theta. In general, the model we are trying to estimate is applied to describe a population with a huge amount of individuals. However, as we know that the population has a large number of individuals, it's impossible for us to know the property of each one. So to get the estimation, what we can do is like we will do in a survey and pick up a small number of individuals as the sample and observe the independent and dependent variables for each individual. And then we can use some statistical method to estimate the population parameters as the theta hat with this n observations in a sample. And theta n is just one estimate of the true parameters in the population. For example, if we are considering linear regression, then g would be the function for the least square operator. Also, the realization of the estimated parameter theta hat is a random variable before we actually get the sample, and this one is applied to estimate the true values. And we should say that the true values is deterministic for the population. Now let's go back to the discrete choice problem. First, we assume that there will be a set of choices available for individual n, and for each choice, it has one utility. For example, for the choice I, the utility is uin, and y would be the observed choice for the individual n. If the choice I is selected, then we can claim that the choice I has the highest utility. Usually, we are considering the probability for the individual n to choose the mode I. It could be represented as the function here, and for the utility, it contains two components: deterministic component v and the random component xi. Considering all the individuals are in the same population, and the population will have the deterministic parameters, then we can assume that all the theta n are the constant coefficients in the model. So we replace it with theta. That is the probability of choosing mode I will be the function of x and the parameter theta. For the MNL model, we will have that the probability of choosing the choice I is exponential of vi over the summation of the exponential vj. Here we say that vj is the deterministic utility. Usually it's a function of theta and x, but we assume that the deterministic utility can be represented by a linear equation. With this assumption, we can rewrite the probability function in this formula. At the same time, Vj would be a vector of the parameter theta times the independent variable x. And this will be the linear format for the deterministic component. In this class, the maximum likelihood estimation is applied to conduct the MNL estimation. First, let's consider the sample with n observations. It contains the independent variable x and dependent variable y. And we know that y is the selected choices. If the alternative I is chosen, then yi is 1. If it's not, that will be 0. Then we can see that there will be only one value for the y vector for each individual, and the summation of all the cells in the y vector would be 1. Also, for this sample, we will have n observations, which means it contains n selections from n individuals. And then we can find out the joint distribution for y1, y2 until we go to yn, with the condition of x1, x2 until we get xn. So it's also straightforward for us to assume that each observation is independent in a sample. Then this joint distribution can be represented as the distribution of each individual, and that would be fy1 given x1 times fy2 given x2, and here we go to fyn given xn. And this is just called the likelihood function. The likelihood function can also be simplified with the product operation. And the maximum likelihood estimation method, we're trying to find out a set of parameters to estimate the deterministic parameter theta. And those parameters will ensure that the observed sample is most likely to be occurred in the population. In that sense, we can have the optimization problem as shown in this equation. We know that the product operation is really hard for us to solve the optimization problem. Then we can introduce the log transformation for the likelihood function. And with that sense, we will have the maximum log likelihood function as shown in this equation. And with this one, the product operation will be modified to the summation operation. In order to solve this optimization problem, we will recall the first-order partial differentiation for the log likelihood function, and it will be applied for all the p plus 1 parameters theta. To ensure that the optimization problem can give us the actual optimal values, we have to make sure that the formula satisfies the second order condition, which means the Hessian matrix must be negative semi-definite. That means all the eigenvalues should be negative. Now let's see how we can apply the maximum likelihood estimation method for the multinomial logic model. This is the likelihood function. It's the product of the probability for each individual n. And with the MNL model, we can find out the probability of choosing the mode I for the individual n. It would be the function of the deterministic utility. And then the probability of yn given xn could be rewritten as the product of I for all the modes, and that will be the probability of I given Cn power to Yin. As we know that for the selection of each individual, if the mode I is chosen, then the value is 1. If it's not, then it's 0. And for this whole formula, we can expand it as the equation here, and that would be the same to the probability of I given Cn. And then we can further expand the likelihood function in this formula, and this would be applied for the MNL model. As we specified previously, the log transformation will be applied for the likelihood function, and this would be steps for us to find out the log likelihood function. First, we apply the log operation for this function, and all the product operations will become the summation. And then we can further simplify the probability power to yin, and it will become yin times the log evin minus the log summation of evjn. This formula can be further simplified. The component here will become vin, and that gives us the formula for the log likelihood function. Then we can further expand the log likelihood as the function of several variables theta. From our previous assumption, the deterministic utility Vj is a linear function of theta and the independent variable x. With this assumption, we can expand the log likelihood function and replacing the Vj and Vi with the linear function, we will have the log likelihood as the function of theta 0, theta 1 until theta p. Then we can use the first order partial differential to find out the optimal value of theta case to maximize the log likelihood for the multinomial logic model. Now let's see how we can find out the first order partial differentiation for this optimization problem. We will try to get the value for partial L over partial theta k, and it could be expanded into two components in the second equation. For the first component, it will be very easy for us to find out the expression. If the index of theta is different, then the partial operation will give you the value of 0. If they are the same, then there will be 1. So for the first component, the value is xkin. For the second part, it's a little bit complicated, but after we do the simplification, we can find that the expression will be very straightforward. It will give us the result as the summation of xkj times exponential of theta times xj over the summation of exponential theta times xj. So that would be the expression for the second component, and this will be the expression for the first one. And then we will have the simplified first order partial differentiation with respect to theta k for the multinomial logic model. The p+1 equation can be rewritten into a vector format. Capital F theta equal to 0. Here F theta is a p+1 vector, and each element in the vector represents one equation with respect to one parameter. We can see that F theta is very complicated, and it's almost impossible for us to find out the analytical solution to the equation. So instead of the analytical solution, we are trying to use some heuristic method to get out the optimal values of theta. So one popular method is called the NewtonRaphson algorithm, and it's based on the recursive Taylor series expansion of the equation. And this formula shows the Taylor series expansion of one function fx is expanded at the point x0. So fx equals to fx0 plus x minus x0 times df over dx at the location of x0 plus half x minus x0 square times d square f over dx square, and so on. For our case, we can apply Taylor series expansion for the vectors. So we will have capital F theta equal to F theta at the optimum value theta m plus lambda F theta at theta m times theta minus theta m plus the other smaller terms. And here lambda F theta represent the gradients of the vector F theta. Also, from the optimization problem, we want F theta equal to 0, and this means we will have the expansion equals to 0. Then we can derive that lambda F theta times theta minus theta m is approximately equal to minus F theta at theta m. And then we can further solve this equation, and it will give us the result as theta minus theta m equal to minus lambda f theta inverse times f theta. It will also give us the value as the true value theta is approximately of theta m minus lambda f theta inverse times f theta. And this would be the equation for us to apply the heuristic method to get the true value of. So here's a step for us to apply the Newton-Raphson algorithm to find out the optimal values of theta. First, we'll set the initial guess of theta. For all the p plus 1 parameters, their initial value can be set as 0. And then we will calculate the refinement to the initial guess using the recursive formula. That is theta m. That will be the parameter we're gonna estimate for the next iteration equals to theta m minus lambda f theta m inverse times f theta m. And here you need to find out lambda f theta m, which is the most difficult part for this iteration. And you will continue the second step until you find out that the differences between theta m plus 1 and theta m is smaller enough, which means the parameters are converged in the iteration. Then you can stop the iteration, and then you will have the estimation for the parameters. In this estimation, the most difficult part is the gradients of f theta. So in the next page, we will show how to find out the elements in this matrix. That is partial FL over partial theta k. From our previous analysis, we have the expression of FL theta, and then it's easy to write down partial FL over partial theta k. In this equation, we just need to find out the expression of partial probability J over partial theta k. With the MNL model, we can define the probability of choosing mode J as the formula here, and then we can apply the knowledge of calculus to find out the partial differentiation. The expression can be further expanded in the second formula. And this formula can be further simplified. We can see that on the top, for this term, it will becomes xkj times exponential of theta xkj, and for the second term, it will becomes xkq times exponential of theta times xq. And now we can do a slightly modification about the index at the bottom and reformat the whole expression. In this equation, you will find that the first term is just the probability of choosing mode J, and similarly for the second one, and for the third term here is the probability of choosing mode Q. Then we can simplify this equation as the xkj times the probability of J minus probability of J times the summation of xkq times the probability of Q. And we can take the probability of J outside the brackets. This one will give us the simplified result for the partial FL over partial theta K. Also, you will find that the index I is not related to any index in these summations. So we can take the summation of yin outside. Another thing you should recall that for the same individual n, the summation of all modes for yi, the result will be 1. Then we can discard this term. And this will give us the final expression for partial FL over partial theta K. For now, we have complete analysis of the MNL estimation. And then we will see one example about using the method to estimate the parameter values. In the model estimation, we have to find out the vector of capital F theta. And from our previous analysis, we can get a general expression of FL theta. In this specific example, there are only 2 parameters to calibrate. Then the size of F theta is 2. And considering the 2 mode, bus and car, applied in this example, this vector can be further expanded for the 2 modes and the 2 different probabilities. Then we can apply the probability of the two driving mode current bars and apply them in the f theta vector. And this would be the full expression about the vector capital F theta with respect to the parameter theta 0 and theta 1. The next thing we will do is trying to find out the gradient of capital F theta and apply the gradient for the NewtonRaphson algorithm. In this example, there are two parameters to estimate theta 0 and theta 1. Then the size of lambda f theta is 2 by 2. And this formula shows the general expression of each element in the gradient matrix. For this example, we are considering two modes, current bars. Then we can further expand the general expression for this specific example as we show in the formula here. Then we can find out expression of each element in the gradient matrix. And this one shows the formula for partial f0 over partial theta 0. And similarly, we can get a partial f0 over partial theta 1. Partial f1 over partial theta 0. And then finally, we have partial f1 over partial theta 1. Summarizing all the results, we'll get a matrix for lambda f theta. Also, previously, we already derived capital F theta for theta 0 and theta 1. Finally, we can apply the equation here to update theta values with lambda f theta and f theta that we derived previously. Remember that you have to apply enough number of iterations to make sure that theta is converged. And the converged theta value would be the estimate of the parameters in the population based on the MNL model.